I'm Daan Reinders. I'm a PhD candidate at Utrecht University, and I'm presenting our research on simulating Lagrangian subgrid-scale dispersion on neutral surfaces. This is a collaboration with Erik de Leersnijder from Louvain and Erik van Sebille, also from Utrecht University, my supervisor. So eddies are very important in the dispersal of material in the ocean. And to illustrate this, I want to show you two simulations of a patch of Lagrangian particles. For this, I use a very popular idealized setup of the Antarctic circumpolar current, a channel model in MIT GCM. On the left-hand side, we use a 5-kilometer resolution model in which the mesoscale eddies are resolved. And on the right, we use a 50-kilometer resolution in which the eddies cannot develop. It's in 3D and depth is indicated by color. So if I start the simulation, you see already quite quickly that in the left figure, in the 5-kilometer case, the eddies stir around all of these particles and they reach many more locations in the domain, whereas in the no eddy case, there's no dispersion at all. So if we have coarse flows in which we want to simulate Lagrangian particles, we need to account for the dispersion due to the unresolved eddies. How can we do this, and how can we do this in 3 dimensions? That's what we'll be looking at here. First, we need to look at the Eulerian case. So here I show the advection diffusion equation that shows or that governs the evolution of a Eulerian tracer. And usually we say that after we have some Reynolds averaging, that the turbulent eddies that are filtered out behave like diffusion, or at least some flavor thereof. And we can actually create a translation from this Eulerian frame to the Lagrangian frame. We can do this by treating the advection diffusion equation as a so-called Fokker-Planck equation, which describes the evolution of a probability density function corresponding to a stochastic differential equation. So in this case, C, which in the advection diffusion equation is the concentration, is then interpreted as a probability density function of a particle being located at position x. Then individual particles will obey the related stochastic differential equation below. So let's pick this equation apart. The evolution of a particle's position then depends on the mean flow. We include a drift correction term, which accounts for gradients in the diffusivity tensor, K. And we have this random walk term. This random walk is actually proportional to the diffusivity. This dW term is a normally distributed random noise term. This dispersion model actually goes by several names. It's sometimes called the random walk model, since we have a random walk on particle positions. It's also sometimes called simply diffusion, due to the link with the advection diffusion equation. And it is also referred to as the 0th order Markov model, where Markov corresponds to the Markovian property that successive displacements in space are completely uncorrelated. They're independent of each other. But this is precisely one of the issues with Markov 0. It produces unrealistic trajectories because the successive displacements of a particle are all independent of one another. So a particle has no memory of its previous turbulent displacement and will move in different directions at every time step. If we look at advection in the fine resolution MIT GCM channel model, we get these trajectories that are shown here. But then if we coarsen the fine flow field and add on top of that the Markov 0 model to account for the missing dispersion, then we get these very erratic trajectories with particles moving in these very angular motions. So the turbulent velocities should actually be autocorrelated in each time step. This is also what we see in observations. Here you see the autocorrelation in velocity of subsurface floats in the western North Atlantic, and we see that the autocorrelation actually slowly decays or exponentially decays over time. This happens with a decay timescale TL. TL is also referred to as the Lagrangian timescale. And this happens at the order of days or maybe a week or so. So Markov 0 actually captures the diffusive regime, which is valid for times much larger than this Lagrangian timescale. This is when dispersion evolves linearly in time. But it completely misses out on the ballistic regime, which occurs when dispersion is quadratic in time, which happens when for times much smaller than the Lagrangian timescale. And this is precisely because the autocorrelation in velocity is missing entirely. Well, there are several models that actually improve on the Markov 0 model. And the one that we're going to look at here is the Markov 1 model that doesn't add random walks on particle positions, but on particle velocities. So the evolution of a particle position, again, depends on the mean flow and on this turbulent velocity, u prime. Now, u prime is then dependent on a decaying autocorrelation, where this tensor theta prescribes the exponential decay timescale, so the Lagrangian timescale, in each direction. There's again a drift correction term, and a random increment where this tensor b contains information on the velocity perturbation strength, nu squared. For times that are much larger than the Lagrangian timescale, we again have that this model behaves like diffusion. So actually we can compare the Markov 1 model and the Markov 0 model at large timescales, and they would behave the same. But the Markov 1 model takes into account the decaying autocorrelation and is also able to capture the ballistic regime. Previous studies of the Markov 1 model, or previous studies that apply the Markov 1 model, have been restricted to the surface so far. So we want to look at 3 dimensions. So how can we actually achieve this? Well, eddies mostly disperse material in 2 dimensions, but not horizontally, but along sloping surfaces of neutral buoyancy, so-called neutral surfaces. And the dispersion in the perpendicular direction, the dianeutral direction, is orders of magnitudes weaker. In the Southern Ocean, the slopes of these neutral surfaces can be quite significant. This also happens in other regions, but I've included a little sketch of the Southern Ocean here from Morrison et al. So now if you want to apply the Markov 1 model in 3 dimensions, you should take the following steps. First, we assume homogeneity and isotropy in the neutral plane. So we don't account for any variations in what the dispersion looks like at different locations along the neutral surface. We assume it's all the same, also in each direction. Then we find Lagrangian timescale TL and the velocity variance nu squared, both as constants or parameters that characterize the dispersion in the full domain. In the perpendicular direction, we assume that the autocorrelation rapidly decays, the velocity autocorrelation. So instead of TL, we have this epsilon TL, where epsilon is a small parameter, and we have something similar for the turbulent velocity. So we use this eta as a small parameter here. Then this allows us to determine the theta and b tensors in the isoneutral frame. And then if we assume that the neutral surfaces are locally flat, using the neutral slopes, which you will have to compute somehow, we can perform a coordinate rotation from the isoneutral frame to the geopotential or XYZ frame for the use in our Markov 1 model. So this is actually similar to the coordinate transformation that Rady used for formulating the isopycnal diffusion tensor back in 1982. Now, we also did some experiments. As the reference case, we used the 5-kilometer resolution MIT GCM channel model of the Antarctic circumpolar current, in which the eddies are resolved. And we coarsen this both in space and in time. So in space, we go from 5-kilometer resolution to 50-kilometer resolution, and we do a time averaging to filter out any eddies. And this will be our test bed for the Markov 0 and Markov 1 model. If we look at the velocity autocorrelation in the fine resolution model, we estimate, and we do this very roughly, an exponential decay with a timescale of 20 days. There's also some oscillatory component, but we'll ignore this here. So what we did is we used this Lagrangian timescale of 20 days to drive the Markov 1 model, and we find that the Lagrangian timescale is recovered in this autocorrelation, especially in the x direction. In the y direction there are some differences, but this is because of boundaries. We also looked at the absolute diffusivity, which is approximately 15,000 meters squared per second, so that's very vigorous. And we find that the Markov 1 model, using the parameters that theoretically should reproduce this absolute diffusivity in the large time limit, do so pretty well, at least in the x direction. Again, boundaries play a role in why this value isn't reached in the y direction, and in the x direction it's also actually a little bit lower, but we give a possible explanation for this in our paper. Now, let's also look at some actual trajectories. In figure A, you see trajectories of particles advected using the fine or the high resolution flow field. And in B, you see trajectories of particles that were only advected using the coarsened version of the flow field, so with no eddies. And this again shows the need of a dispersion parameterization. So we added both the Markov 0 model and the Markov 1 model on top of this. In C, you see the Markov 0 model, which is what we showed earlier, and then in D, you see Markov 1. And if we compare both to what we see in the fine advection case, it's clearly that the trajectories in using the Markov 1 model are a lot more realistic. To summarize, Lagrangian dispersion is usually parametrized using a random walk, which is equivalent to diffusion in the Eulerian case, but this is overly simplistic because particles have no memory at all and successive displacements are completely uncorrelated in directions. So an improvement would be to actually add this exponentially decaying velocity memory term, which we saw in the Markov 1 model. We apply this Markov 1 model in 3D, and we take into account that eddy dispersion happens predominantly along neutral surfaces. So actually we formulate everything in the neutral frame. We assume homogeneity and isotropy in the isoneutral frame, and we do a coordinate rotation, just like Rady did for the isopycnal diffusivity tensor. So if you want more realistic dispersion in three-dimensional Lagrangian simulations, then use our method. There's also a lot that I left out here, but you can read more about this in our paper. So one thing, for instance, is how can you estimate these parameters, nu squared and the Lagrangian timescale TL. We also find, very surprisingly, that Markov 1 has a smaller spurious diapycnal or dianeutral diffusivity than Markov 0 does. You can also read a lot more about this in the paper. And we tested a closure-based parameterization that we use in the Markov 0 model. This was formulated by Le Sommer in 2011. So if you're curious, then feel free to scan this QR code or just Google the title of our paper, of this talk, because it's the same as the title of our paper. Thanks for listening.